Welcome back. We've spent the last few units watching ions race like sprinters and surf like pros. We've mastered the golden ruler and the high-speed wave. But today, we're going to do something that sounds almost impossible. We aren't going to watch the molecules fly. We are going to make them stay. Imagine a fountain where a ping-pong ball sits perfectly suspended in the jet of water, unmoving, defying gravity. That is the logic of trapped ion mobility spectrometry, or TIMS. Welcome to the molecular park. Today we move from the strategy of flying to the strategy of parking. Have you ever tried to herd cats? Or catch a single snowflake in a blizzard? In traditional chromatography and IMS, we are always chasing the signal as it flies past our detector. But a specialist knows that sometimes, the best way to see the truth is to press the pause button. In TIMS, we don't just measure a race, we manage a parking garage. We are going to learn how to trap ions in a 100 meter per second wind tunnel and release them with surgical precision. It's time to take strategic control over molecular motion. To master this technology, we navigate 4 strategic sectors. Sector A, the push-pull logic, how we use wind and electricity to fight a battle of equilibrium. Sector B, the power of accumulation, why trapping means we stop throwing data away. Sector C, ramping the truth, the art of controlled release for ultimate resolution. And finally, Sector D, PASEF, the ultimate efficiency engine for proteomics. Let's start with the standoff in the tunnel. In a TIMS analyzer, we have 2 opposing forces. First, we have a massive gas flow, a 100 meters per second wind pushing the ions forward. If we did nothing, they'd be gone in a millisecond. But then, we apply a DC electric field gradient pushing in the opposite direction. Specialists' insight. It's not a race, it's an equilibrium. Every ion finds its specific parking spot, where the force of the wind, which depends on the ion's shape or CCS, perfectly matches the force of the electric field. Look at the geometry. A big, bulky ion with a large collisional cross-section catches more wind, like a sail on a boat, and gets pushed further down the tunnel. A small, sleek, compact ion feels less drag and parks earlier in the gradient. We've effectively sorted our molecules by shape in 3D space. Actually, think of this as a molecular parking garage. Every car has a reserved spot based on its aerodynamics. We have turned a time-of-flight problem into a spatial distribution solution. Here is where TIMS leaves the competition behind. In a drift tube, if you aren't ready to detect an ion, it's lost to the vacuum. But in the molecular park, we can hold the ions while the detector finishes its previous task. This is ion accumulation. While we are releasing one group of ions, we are already catching and parking the next group in a parallel trap. We call this a 100% duty cycle. We are no longer throwing sample away, we are harvesting every single pulse. This is how TIMS achieves sensitivity gains that were previously impossible. Once the ions are parked, how do we get them out? We lower the electric field barrier slowly. We call this the electric field ramp. As the pull weakens, the wind pushes the ions out one by one into the mass spec, starting with the largest CCS first. Mentor's tip. Actually, the slower you ramp, the higher your resolution. In a TIMS device only 5 centimeters long, we can achieve resolving powers greater than 250. It's like a slow-motion replay of a photo finish. It gives you absolute structural certainty. But here is the consultant's strategic trade-off. Precision is always a choice. A very slow ramp gives you the ultimate resolution to separate 2 nearly identical isomers, but it slows down your run. A fast ramp keeps up with your high-speed LC peaks, but sacrifices some shape clarity. A specialist architects the ramp slope to match the complexity of the sample. You don't just follow a protocol, you design the physics of the release. This is where TIMS becomes a factory. Parallel accumulation, serial fragmentation. Because we release ions in ultra-sharp, concentrated packets from the trap, the mass spectrometer can fragment 10 different precursors in the time it used to take for one. We are stacking our data. Consultant's secret. This is how we identify 10,000 proteins in a single run. We aren't working harder. We are managing the queue, so the mass spec detector never spends a microsecond waiting. We are maximizing the ROI of every ion created. Have you ever felt like you were losing your sample because it was too complex and the peaks were flying by too fast? TIMS is your pause button. It holds the complexity in place, sorts it by shape, and then hands it to the mass spec in a perfectly ordered line. It's the difference between a chaotic crowd trying to enter a door and a VIP procession. It turns the noise of complexity into the music of discovery. Summary: the mastery of the park. We've moved from racing to parking. You now understand the push-pull equilibrium, the 100% duty cycle of accumulation, and the resolution power of the ramp. Remember the specialist's mantra: don't just watch them fly, make them stay. Control is the mother of resolution. You now have the power to resolve the unresolvable. You've mastered the park. But what if the park is full of trash? What if chemical noise is burying your signal? Join me in our next unit, Module 4-9, the background filter, where we use FAIMS to scrub away chemical noise using high-field shutter logic before it even hits your analyzer. We're going to clean the house before we start the analysis. I'll see you at the starting line of the next module.